Geometric series. Let's start by defining a geometric series. A geometric series is of the form a plus ar plus ar squared plus ar cubed, and so on, where the relationship between consecutive terms is that we're multiplying by a copy of r each time. So to get from a to ar, we multiply by r. To get to ar squared, we multiply by another copy of r. To get to ar cubed, we multiply by another copy of r. So a and r are real numbers, and r has a special name. It's called the common ratio. If we want to express this in summation notation, we can start with an index of 0, and our general term will be ar to the n. So if we think about substituting in 0 into n, r to the 0 would be 1, making our first term be just a. And then, of course, we'd substitute in 1, so we'd get ar. Then we'd substitute in 2, and we'd get ar squared, and so on. But we could also choose a different starting index as long as we modify the general term. So let's say we want a starting index of 1. If we want to make sure that our starting term is just a, then we need to make sure that the exponent ends up being 0 so that we end up with r to the 0. So our exponent needs to be n minus 1. So when we substitute in 1, we get 0. R to the 0 is 1, and all we have left is a. So we can start with a different index as long as we modify the general term. Now, what is really powerful about recognizing when you have a geometric series is that you can determine, just based on the r value, the common ratio, whether that series converges or diverges. So it turns out that if the absolute value of r is less than 1, the series converges. And more powerful than that, it converges to a over 1 minus r. So we can find the value that the infinite series converges to, where a is the first term of the series and r the common ratio. If the absolute value of r is greater than or equal to 1, the series diverges. So we have nothing inconclusive about it. If we have a geometric series, all we need is that value of r, and we can determine whether the infinite series converges or diverges. First, let's make sure we can recognize when we have a geometric series. So here we're being asked which of the following are geometric series. Let's remind ourselves of the nicest version of summation notation of a geometric series, the sum from n equals 0 to infinity of a times r to the n. Now, we might not have something that looks exactly like this, but what we're looking for is a to be a number, r to be a number, and then up in the exponent here, that's where the indexing variable is going to be, to the first power. But we may need to do a little bit of rewriting if we want it to look like this form here. Let's start with this first example, the sum of n equals 0 to infinity of 2 times 1/3 to the n plus 1. So this one is a geometric series, and it has the form that we're looking for, where this is a number here, this is a number here in the base, and there is an n, the indexing variable, up in the exponent raised to the first power. Now, it's not exactly like this. So here the starting index is 0, and the exponent up here is n, but here we have n plus 1. But this would still qualify as geometric. If you want to see the little bit of algebra it would take to rewrite it to get it to look exactly like this, here's what we can do. We can write this as the sum of n equals 0 to infinity of 2 times 1/3 to the n times 1/3 to the first. So I can basically rewrite this and because the exponents add back together. But now this 1/3 can be multiplied by the 2 in the front, and then I have the sum of n equals 0 to infinity of 2/3 times 1/3 to the n. Now this has its advantages because now this value here in front is the starting value. This is the first term, because when you substitute in 0 now, this whole thing becomes 1. So 1/3 to the 0 is 1. And so what we have left over is 2/3 as the first term. So this has its advantages, but it's not difficult to find the first term by just substituting 0 into the original summation. So if I do that, if I substitute in 0, then the exponent here is 1, and I have 1/3 times 2. Okay, well, that's just 2/3. So I wouldn't say that it's necessarily worth it to rewrite it just to get it in this form. Again, we want to be able to recognize when we have a geometric series without necessarily having to write it exactly in this form. So on this next example, I have the sum of n equals 0 to infinity of 7n cubed. This one is not geometric. So here, the problem is that we do have 7, a number, first, but then I have n, the indexing variable, raised to a number. So it's the opposite of what I want. What I want is a number in the base, and then n, the indexing variable, in the exponent. So here, basically, this looks like a polynomial, and what I really want it to look like is an exponential function, right? Exponential functions have the variable up in the exponent. All right, the third example, the sum of n equals 1 to infinity of 1/4 times 4 to the 2n. So this is also geometric. And what we're looking for again is that number in front and then a number in the base. So we have 4 in the base, and then in the exponent I have n to the first power. So it's okay that it has a 2 there, although that is going to affect what the value of r is. So here the value of r is not 4. What we would have to do to recognize the value of r is we'd want to rewrite this as 1/4 times 4 squared to the n. So by our properties of exponents here, this is true. So the 2 times the n would get us back to the original, but we want to choose to keep the 2 as the exponent of 4. So 4 squared is 16. So my summation is actually n equals 1 to infinity of 1/4 times 16 to the n. So again, this is geometric, but that r value would be 16, not 4, because I do need it to be to the power of n. To the first positive n, I can't have that 2 in the front. Now here, just a quick note, the first term is not 1/4. In order for the first term to be this number in front, I would need this to 0 out when I substitute in my starting index. So I would need it to have this form here, right? N equals 1 to infinity, ar to the n minus 1, and this is just to the n. But I wouldn't necessarily say it's worth it to rewrite it. We can find the first term by always just substituting in the starting index. So if I substitute in 1, then I'm going to have 16 times 1/4, so just 4. If we want to just practice the algebra there of working with exponents, which is important, I would just factor out a copy of 16 in order to get that n minus 1. So I'd have 1/4, 16 to the 1, and then what would be left is 16 to the n minus 1, because I took out one copy of that. And then the 1/4 and the 16 are going to create that 4 that we said already was the first term. Moving on to the fourth example, the sum of n equals 1 to infinity of -3 to the n. Yes, this is geometric. We have a number in the base, right? And then the n in the exponent. We have number in front. Technically, it's 1. And so this absolutely checks out. This is geometric. The next example, the sum of n equals 1 to infinity of 5 to the n squared. This one is not geometric. So although I have a number in the base, 5, I don't have just n to the first up in the exponent. So remember, the true definition here is that to get from one term to the next, we're always multiplying by the same number. So let's write out a few terms here just to prove to ourselves that this doesn't work with that n squared as the exponent. If I substitute in 1 into n, then my first term is 5, plus if I substitute in 2, 2 squared is 4, so I'd have 5 to the 4th, and then plus if I substitute in 3, I'd get 3 squared is 9, so I'd have 5 to the 9th next. Now let's just check. To get from 5 to the 1st to 5 to the 4th, I'm multiplying by 5 cubed. And then to get from 5 to the 4th to 5 to the 9th, I'm multiplying by 5 to the 5th. So this does not have a common ratio, so it is not geometric. And you can convince yourself the second one is not geometric using the same reasoning by writing out the expanded summation. And finally, the sum of n equals 0 to infinity of 4 times 3 to the negative n. So I have a number 4, I have a number in the base 3, and then n to the first in the exponent, but I have a negative there. So is this still geometric? Yes, it is. I can think about this as n equals 0 to infinity of 4, and then 3 to the negative 1 times n. I'm showing kind of a lot of work here. Here, that negative n is negative 1 times n. And what do we know about 3 to the negative 1? We can rewrite that as 1/3. So I have 1/3 to the n there. So n equals 0 to infinity of 4 times 1/3 to the n. Yes, this is absolutely geometric. So we're just looking for a number on the outside, a number in the base, and then n to the first in the exponent. There could be a number multiplied by that n, even a negative, or a number added or subtracted, but I cannot have something polynomial-like or a higher power of n in the exponent. Now let's get to some examples. We're told here the following series are geometric. Find their first term and common ratio r, then determine if the series converges or diverges. If it converges, find its sum. So here, find the first term and common ratio. The first term is just substituting the starting index into the n. So here I'm going to have negative 2 to the 0 is 1, so all that's left is that 3 in front. So we'll say a is equal to 3. And then the r value is the one raised to the n here. So my r is negative 2. Well, the absolute value of r is what we have to check to determine convergence or divergence. The absolute value of r is positive 2, and that's greater than 1. If the absolute value of the common ratio is greater than 1, then the geometric series diverges. Now, I've gone ahead and just told you that's the case, but let's try to understand why the common ratio, the absolute value of that common ratio being greater than 1 makes the series diverge. Let's expand this out for a second. So we said the starting value was 3 and the common ratio is negative 2. So to get to the next term, I'll multiply by negative 2. That's going to give me negative 6. Multiply by negative 2 again, that's going to give me positive 12. Multiply by negative 2 again, that's negative 24. And then positive 48, and so on. So let's think about whether it makes sense for this sum to actually be a finite number. Well, no, if we look at the individual values, regardless of sign, just those individual values are getting bigger and bigger and bigger. So here, if we were to actually perform the test for divergence, these are going to be bouncing back and forth between positive and negative, but the absolute value of those numbers is they're getting bigger and bigger. So the limit as n approaches infinity does not exist. And so if the numbers aren't even getting smaller or closer to 0, then there's no way that the sum can converge. So hopefully it makes intuitive sense why we would say that if the absolute value of the common ratio is bigger than 1, that the geometric series diverges. Now we have the sum of n equals 1 to infinity of 4 over 3 to the n. So we know this is geometric, we're told that it is. We want to find the first term, so let's substitute in 1 into n. So we're going to have just 4/3. So my a value is 4/3. And then we need to find the value of r. What we're going to do is we're going to rewrite this as the sum of n equals 1 to infinity of 4 times 1 over 3, all raised to the nth power. Remember that 1 to the n is going to end up being just 1 every time as we substitute in, 1, 2, 3, etc. So I can think about this as 1 to the n over 3 to the n. So I can now more clearly see that r is just 1/3. So r is 1/3 here. The absolute value of r is obviously still 1/3, which is less than 1. So this geometric series converges. And more than that, we can find what it converges to because it's geometric. So this infinite series is going to add to, it's going to equal that first term, 4/3. So 4/3 over 1 minus that common ratio r. So over 1 minus 1/3. So that's 4/3 over 2/3. And That's 4/3 times the reciprocal, 3/2. The 3's cancel. 4/2 is just 2. So this infinite geometric series converges, and we know it converges to 2. Now, one more time, I want us to just make sure we can at least justify in our own mind why we need the absolute value of the common ratio to be less than 1 for this series to converge. Let's write out a few terms. We know that the first term is 4/3, and to get to the next term, we'll multiply by a third, so that would give us 4/9. And then the next term would be 4/27, and then 4/81, and so on. So hopefully we can see, again, that we're multiplying by 1/3 each time. But another way to think about multiplication by 1/3 is division by 3. So these terms are getting small, but that's not enough, right? We don't just need the numbers to be approaching 0. We need to know that they're getting small enough fast enough. So it turns out that here, the numbers are getting small enough fast enough to end up being a finite number, even though we're adding up infinitely many terms. Here we have 5 minus 10/3 plus 20/9 minus 40/7, and so on. We want to find the first term. Well, we can see that here is clearly just a is equal to 5, but then we also need the common ratio. So we're going to need to do some work for that and think about what number are we multiplying by here, but from each term to get to the next. So the first term is 5/1, and so it starts positive and then the next term's negative. So our common ratio is going to have to be a negative value. Across the numerator, I'm multiplying by 2 each time. So I'm going to have a 2 on top there. And in the denominator, I'm multiplying by a 3. So I'm multiplying by negative 2/3. So my r value is negative 2/3, and the absolute value of r is 2/3, which is less than 1. So if the common ratio is less than 1, then we know that the geometric series converges. And more than that, we know what it converges to. So this is going to converge to the first term, 5/1 minus the common ratio. So here we want to be careful. We want to take the common ratio with its sign. We want to take negative 2/3 with us here. So 5/1 minus negative 2/3, that would become plus. So we're going to have 5/1 is 3/3 plus 2/3 is 5/3. And then let's write that as 5 times the reciprocal of 3/5. So the 5's cancel, and we know that the sum is just 3. Notice that we did not have to write this in summation notation, although if we wanted to, it would be pretty easy because we already have a and r. So we could write the summation notation n equals 0 to infinity of 5 times r, negative 2/3, to the n. We have that starting index of 0 and that power of n here. When we substitute it in, we get that starting term 5. Here we have the sum of n equals 0 to infinity of the square root of 2 times pi over e to the n. So if we want to find the first term, we would substitute 0 into the n, so that whole thing is 1, and all that's left is a is equal to radical 2. Now, the value of r is pi over e. Remember, that's just a number. And if we think about the absolute value of r, well, it's already positive, so we get pi over e. And we have to decide whether that's less than or greater than 1. Pi is approximately 3.14, and e is approximately 2.71. That means that this fraction is greater than 1. So if the absolute value of r is greater than 1, then we know that the geometric series diverges. So it turns out we really didn't need the value of a because we're not going to find its sum if the series diverges. On this example, we want to determine if the series converges or diverges. If it converges, find its sum. We have the sum of n equals 0 to infinity of 2 to the n minus 3 all over 4 to the n. What we're going to do to start this problem is we're going to go ahead and split this up. So we're going to rewrite it as the sum of n equals 0 to infinity of 2 to the n over 4 to the n minus 3 over 4 to the n. So now we can see that our general term is a difference. And because a summation is just adding up a bunch of terms, we can distribute a summation over addition or subtraction. So in other words, we can rewrite this as two separate series. So we can say the sum of n equals 0 to infinity of here 2 to the n over 4 to the n will be 2/4 to the n. Well, 2/4 is 1/2, so 1/2 to the n minus another series n equals 0 to infinity of 3 times 1/4 to the n. So I'm rewriting this so that we can see that these are both geometric, and we would need both of them to converge in order to say the original series converges. Let's look at each one separately now. This one on the left, the r value is 1/2. So we have r is equal to 1/2. The a value is, if I substitute in 0, 1/2 to 0 is 1. So my a value over here is 1. R is 1/2. The absolute value of r is still 1/2, which is less than 1. So this geometric series converges. And then over here, I'm not actually going to find the sum yet, because if this one doesn't converge, then there's really no point. But let's check. So if I, in the first term, if I substitute in 0, I'm going to end up with 3, just that number in the front for this one. And then the common ratio is 1/4, which the absolute value is just 1/4, which is less than 1. So yes, this is geometric and also converges. So because they both converge, the original series converges, and we can find what it converges to. So this first one would be a over 1 minus 1/2. So 1 over 1/2. If I multiply it by the reciprocal, that's 2. Minus, over here, my first term is 3 over 1 minus r is 1/4. So that's 3 over 3/4. If I multiply by the reciprocal of 3/4, that's 4/3. And the 3's will cancel, so we'll actually just end up with 4 here. So 2 minus 4 is -2. So the original series converges to -2 because each of these individual series were geometric with absolute value of r less than 1, and so they converged. This next example is kind of different. It's asking what value or values of x make the following converge. Find the sum of the series in terms of x. All right, so here I have the sum of n equals 0 to infinity of 3 times the quantity 2x minus 1 to the n. So I have this x in here, and we're asked what values of x make the following converge. Let's actually substitute in a number for x just to understand what is happening here. So if let's say let x equal 0, our sum is going to be n equals 0 to infinity of 3 times, inside here, I'm going to have -1 to the n. So I have a geometric series. My r value would be -1. So I'd have r is -1. The absolute value of r is 1. And if our r value is either greater than or equal to 1, then my geometric series diverges here. Okay, so what values of x make the following converge? Not 0, right? When I substituted in 0, I got out a common ratio absolute value of 1, and so that doesn't work for a geometric series. So what values do work? Well, we're not going to try every single x value. What we want to recognize is that here the 2x minus 1 is in the place of r. This has that a r to the n look. So in order for this to converge for different x values, what we would need to do is we would need to solve when does the absolute value of r, when does the absolute value of 2x minus 1 satisfy the inequality of being less than 1? Because that's how we know a geometric series converges. So we're going to solve this for all the x values that work. Okay, so how do we solve this linear absolute value inequality? Well, we can drop the absolute value bars if we trap 2x minus 1 between -1 and 1. So -1 is less than 2x minus 1 is less than 1. Then we'll add the 1. This is a 3-part inequality. We'll add 1 everywhere. So -1 plus 1 is 0 is less than 2x. So I added 1 here. And then if I add 1 on the right, 2. And then let's divide everything by 2. So 0 divided by 2 is 0. 2x divided by 2 is x. 2 divided by 2 is 1. So now I have this set of values. This set of x values between 0 and 1 are the ones that make this converge. So this is my answer. Let's check, right? Let's pick a value in this interval. I'm going to go ahead and pick, let's say, what's right in the middle here, just 1/2. So if I substitute in x is equal to 1/2, now I'm going to have the sum of 3 times 2 times 1/2 minus 1 to the n from n equals 0 to infinity. Well, that's 3 times, ooh, this is interesting. So 2 times 1/2, that's 1. 1 minus 1 is 0. 0 to the n, that's just 0. So I'm adding up 0 infinitely many times. Does that converge? Yeah, it does. I mean, it's boring, but it does. It ends up just being 0. So yeah, 1/2 works. Let's try a different value because that was kind of boring, right? Let's try 1/4. So if I let x equal 1/4, I have the sum 3 times the quantity 2 times 1/4 minus 1 to the n. That's 3 times 1/2 minus 1 to the n, or 3 times negative 1/2 to the n. All right, now this is more interesting, right? So r is negative 1/2. The absolute value of r is 1/2. That's less than 1. So yes, this converges. The value of 1/4, which is between 0 and 1, did work out. So I just want us to get a good understanding of what we're doing here when we're finding these x values that make the following converge. So that's the first part of the question. Now find the sum of the series in terms of x. Find the sum of the series in terms of x. Well, we know that the sum of a geometric series is a over 1 minus r. So here, this infinite series converges for values between 0 and 1. And what does it converge to? So a, the first term, if I substitute in 0 into n, this whole thing becomes 1, so I just get 3. So 3 over 1 minus r. What was r? R was this 2x minus 1. So I'm going to put 2x minus 1 here. Let's simplify that a little. 3 over 1 minus 2x plus 1, or 3 over 2 minus 2x. So for values of x between 0 and 1, this converges, and it converges to 3 over 2 minus 2x. This is going to be a really important problem for the future of all of this series stuff. So on this one, we want to do the same thing. Find the value or values of x that make the following converge, and then find the sum of the series in terms of x. This one looks a little bit uglier, but this one is also geometric. We just have to mess around with it a little bit to find the value of r. So I have n equals 0 to infinity of, we have x minus 3 to the n. In the denominator, I'm going to rewrite 2 to the n plus 1 as 2 to the n times 2 to the 1. And then I'm going to write this as the sum of n equals 0 to infinity of 1/2. So this 2 in the denominator, I'm kind of pulling it to the front, thinking about it as 1 over 2. And then x minus 3 over 2 is all raised to the n. So I'm taking that part in the numerator and denominator raised to the n and turning it into this one fraction raised to the n. So my r is x minus 3 over 2. So what I'm going to need to do to find all the values of x that make this geometric series converge, I'm going to need to solve when is the absolute value of r, which is x minus 3, over 2, less than 1. So what I can do on this one is I can actually pull the 1/2 out of the absolute value bars and then multiply by 2. So I have absolute value of x minus 3 is less than 2. I'm multiplying by a positive, so that doesn't change the inequality. And then now to drop the absolute value, I can say this is negative 2 is less than x minus 3 is less than 2. I can turn it into a 3-part inequality. And then I'm going to add the 3 to all 3 parts. So negative 2 plus 3 is 1, is less than x, is less than 5. So all of the values between 1 and 5, not including 1, not including 5, those are values that make this series converge if I substitute them in. And when what do they converge to? Okay, well, they're going to converge to a over 1 minus r. So what's a? If I substitute 0 into this n and this n right here, this whole numerator would be 1 and the denominator would be 2. So I could substitute it in up there, or this nicer, cleaner version down here helps me see it. where this whole thing is raised to the 0, all I have left is 1/2. So 1/2 over 1 minus r. Ooh, so r is this x minus 3 over 2. Now I don't want to leave a complex fraction, a fraction within a fraction, so I'm going to clear fractions by multiplying the top and bottom by 2, and that 2 would distribute to the binomial on the bottom, leaving me with 2 times 1/2 in the numerator 1, and then 2 minus x minus 3. So the 2 distributes here. Here the 2's cancel, but that negative still applies to the entire binomial. And then I'm going to have 1 over 2 minus x plus 3, or 1 over 5 minus x. So this is the sum in terms of x, and it only works when I substitute in x values that are between 1 and 5. And now we're going to go back to just looking at geometric series, finding their common ratio, and determining if they converge or diverge, and if they converge, find the sum. And the only difference here is that some of the algebra is a little bit more involved just to practice the algebra. So here we're going to rewrite this as the sum of n equals 1 to infinity of 3 to the n times 3 to the 1 over 2 to the 2n times 2 to the negative 1. Now this is going to be the sum of n equals 1 to infinity of 3 times 3 to the n, and then 2 to the negative 1, we can move to the numerator and it would become 2 to the positive 1. And 2 to the 2n, we could group as 2 squared to the n, so that's a 4 to the n. So this is actually the sum of n equals 1 to infinity of 6 times 3/4 to the n. So the 2 times the 3 gave me the 6, and then 3 over 4 to the nth power. So now we can maybe more clearly see that we have a geometric series. So my r value is 3/4. The absolute value of r is 3/4, which is less than 1. So this is geometric and converges. And what does it converge to? So this is going to equal, if I substitute in 1 to get the first term, okay, so let's see here. If I substitute in 1, I'm going to get 6 times 3/4, so that's 18 over 4, or 9 over 2, and then 1 minus 3/4. So what we're going to have is 9 over 2 over 1 over 4. That's 9 over 2 times 4 over 1, the reciprocal, and we can reduce here and end up with a final answer of 18. For this one, the sum of n equals 0 to infinity of -4 to the negative n. So we want to be careful because of that negative n. We want to remember that we can rewrite this as -4 to the -1 to the n, so that -1 and n multiply back together. But now -4 to the -1 is asking me to take the reciprocal of -4, which is -1/4. So inside here, I have -1/4 to the n. And so -1/4, the absolute value of that anyway, so r is -1/4, the absolute value of r is +1/4, that is less than 1. So this is geometric, therefore this series does converge, and we can find what it converges to. If we substitute in 0, -1/4 to the 0 is 1, so my starting value, my first term is 1, and then 1 minus r. We want to use the original value of r, which is -1/4. So 1 minus -1/4, that's 5/4. And then multiply by the reciprocal, so we end up with 4/5. Here we have the sum of n equals 2 to infinity of 4 to the n minus 1 over -5 to the n. So here I have the sum of n equals 2 to infinity of 4 to the n times 4 to the -1 over -5 to the n. Well, 4 to the -1 is 1/4. So this is the sum of n equals 2 to infinity of 1/4. And then -4 over 5 to the n is how we can express the remaining pieces of our general term. So -4 over 5 is our r value. R is -4/5. The absolute value of r is 4/5, which is less than 1. So this geometric series does converge. And now let's see what it converges to. It doesn't matter that the starting index is 2, that's just going to define our first term. So we would substitute 2 into n and see what comes out. So here, if I substitute in 2, negative 4/5 squared, if we want to pull it off to the side, we can. So we're going to have 1/4 times negative 4/5 squared. That's 1/4 times 16 over 25. Okay, so these reduce here. 4 divides into 16 4 times. So 4 over 25 is my first term over 1 minus negative 4 over 5. Okay, so this is 4 over 25 over, if I add the opposite, 1 is 5 over 5, so that's going to be 9 over 5. So this is 4 over 25 times the reciprocal, 5/9. 5 goes into 25 5 times, so I have 4 over 45. Just a little bit more algebra and arithmetic, but the same concept. On this one, we have a decimal thrown in. I have the sum of n equals 0 to infinity of negative the quantity 0.75 to the 1 minus n. Now, what I'm going to do is rewrite the decimal as a fraction. So I'm going to put negative the quantity 3/4 to the 1 minus n. So now I'm going to rewrite this, n equals 0 to infinity of negative, and then I'm going to write this as 3/4 to the 1 times 3/4 to the negative n. And 3/4 to the negative n, we could think about that as 3/4 to the negative 1 all to the n. And in front, I just have negative 3/4. And so here, 3/4 to the negative 1 is going to have me do the reciprocal of 3/4, which is 4/3. So what I really have is 4/3 to the n, and then that negative 3/4 in front. But the idea is that 4/3 is the common ratio, and the absolute value of that is the same thing, and 4/3 is greater than 1. So this is geometric and diverges because the common ratio is greater than 1. Now, on first glance, we might have thought 0.75, that's less than 1, but that negative is what made me take the reciprocal of that and realize that the common ratio is actually greater than 1.